We are now recording. Let's go from current slide. And before we get started today, let me go over just a couple of more things. I guess a little housekeeping to begin with. I have received one paper from this class. We are awfully close to the midpoint. 1, 2, 3, 4 out of 8 weeks. We're at it. Today is the last day of the first half of the mini-term. Okay, so that means you only got 4 more weeks left before the end of the term. Now that includes finals, by the way, so please get your paper in. If you get in the month of November, you still get a bonus point. Okay, October you would have gotten 2. But in fact, maybe did I say 2 bonus points? And before finals week, I'll have to check that. You might actually have some more, but get it in October, in November if possible. Okay. Secondly, I'm putting this on Screencast-O-Matic so everyone can hear. I still have 1, 2, 3 people who've not turned in the first lab. 1, 2. Okay, first test. 1 person who hasn't turned in the first test. Okay. Here's Lacey. Increase the class attendance by 25%. Excellent. Okay. Lab 2, 1, 2, 3. 3 people haven't turned in Lab 2. Lab 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is more than half the class hasn't turned in Lab 3.
I need to get Lab 3.
Okay, I'll get it for you. Say again? Yeah, I would highly recommend it. Okay. Lab 4, 1, 2. 2 people haven't turned in Lab 4. Test 2, 1. 1 person, you're going to take it today, huh? I'll soon be able to turn back test 2, finally, to turn something back. And Lab 5, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8 people haven't turned in Lab 5. Now, we just did this last time, so there's plenty of time to get that in. So please get those done, okay? All right, that's just catching up on that. We'll have a lab today at the end of class, the last 2 hours. It won't take you 2 hours. So you'll get to leave for Veterans Day a little early, okay? So not super early, but a little bit, okay? And then we'll finish the chapter today, chapter 3, meaning the last 30 minutes on Tuesday, we'll have a test. The 2 hours before that, we'll probably have the lab on the first part of chapter 4, first lab in chapter 4. Okay. And then 2 hours we'll have approximately for class. So between today and those 2 hours, we should cover enough material for the first lab in chapter 4. All right, the other things I was going to say, obviously my office hours were shortened today because we had a faculty staff meeting, and I just came from that, so that's why I was a little late getting here. And number 2, tomorrow I'm normally on Birmingham campus, 7:45 to 11:45, but not tomorrow. Veterans Day. Campus closed, school, state holiday, don't show up, okay? You won't find anybody, okay? And that's for tomorrow. Next week should be back to somewhat normal. Now, I hope y'all know about this, that the week of Thanksgiving, not just the days of Thanksgiving, but the week of Thanksgiving, y'all are out, okay? We've got meetings, but y'all don't have to be here that entire week. Okay. So you needed who needs SWOT? Let me get them while I'm going. Okay, all of you I think have had Lab 2, right? Lab 1. And Test 1, none of you are that. Lab 2, the motion lab. Any of you need that? Okay. Lab 3, the projectile motion lab. Not quite the same as motion, but projectile motion. You need that one?
I need 3, 4, and 5.
So there's 3. You need 3? You didn't have that one?
I think this is the one.
Let me see if you're in the book for it. Excuse me.
Yes, sir. I'm ready.
No problem. Lab 3 will, no, I don't have it from you, so I don't know if you got it or
Which
not.
other ones would I not have? I think I don't have 2 also. I'm not
2? Let's see. Lab 2, yep, Will, I don't have yours.
So
Did you not, were you not here that day?
No, sir. I think I'm just missing this one.
Okay,
Thank you very much.
okay,
This last batch number.
just the last.
is 5.
Okay, no one else is missing projectile motion. Okay, how about laws of motion?
Is that 4?
Yeah, that would be lab 4.
I didn't know.
Okay. Front and back. Okay. Test 2 is the one you need, right?
Yes.
I think you had it. Here's your test 2. Okay. And then we had, let me see that test 2, make sure I get you right. Yeah. Okay, working power. I know you did working power, right? You need working power. You need working power? The last one we did?
I think that's the one we did the other day.
Okay. And you need working power. Okay.
This was Tuesday.
Huh? That was Tuesday.
I was going to make sure I did my 6.
The what?
His sheet his sheet did not look familiar to
Projectile
me.
motion.
Which
The number
one?
6?
Projectile motion.
Number 6. Huh?
Projectile motion.
Projectile motion? That one?
Yeah.
That's the one we were in the lab. Let me see if you turned that
I've
in.
been here.
That's lab 3, didn't I say?
I think so.
I don't have it from you. So you didn't do it? Okay. All right. All right. I think we've got that done. And let's see. All right. And then that will be today's lab. All right. Any other questions before we get started? Glad the 4 of you are here. I don't know where everybody else is. Early Veterans Day? I don't know. Did auto program go early today because of faculty meeting? Okay, and some of them may. What's that?
It's just us that are in this class.
Oh, okay. Okay. What are y'all? Toyota?
We're GM.
GM. And what?
I can't keep track of them. I
I'm
don't know.
sorry. I can't hear talk.
She
I
don't
don't know
know
where
where
they are.
Oh, I see. Are you also Toyota? Okay. So there's only, what, 3 GMs? And
2 GM.
2 GMs. You too? That's it? Wow. That's usually one of our bigger classes. Okay.
Yeah.
What's that?
It didn't work out this time, not that way.
I see. All right. Now, where we're starting off today, I got a little carried away and skipped some stuff that wasn't on the slide set. I was going through the slide set last time and missed some of this. So on page 76, if you got the big book, if you got the smaller one, it might be a slightly different page. Science and Society, near the top of the page, grow your own fuel. By the way, that's fuel. And pretty interesting little blurb there. It's not very long, but it really covers quite a bit of material and a few of the things we talked about in class last time. Well worth a read there. Okay. Also, on page 77, or the next page, there's a people behind the scenes, and here they talk about good old James Prescott Joule, okay, who was one that the unit for energy is named after, Joule. Very interesting character. Normally probably wouldn't have been a scientist. Still had a great mind. A couple of things happened. Is number one, this was back at the time, I think it was in Britain, when generally scientists almost were elite, up there. James Prescott Joule was a son of a tradesman. They usually didn't have opportunity to become scientists, but his dad was fairly wealthy, even though he was a tradesman. He ran a brewery, okay? and they made a fair amount of money. And this was about the time when the Industrial Revolution was happening and are just beginning, so he was in on the ground floor of that. But normally he would have just been in the money-making business with his dad, except that he was a sickly child. In fact, there's some indication he may have had hemophilia. So he was like, that's free bleeder, and been very hard for him to do very much manual physical work, because if he ever got cut or something, they couldn't stop the bleeding and he might bleed out. So anyway, so he focused on academics and became one of the top scientists of the day. Of course, the elite didn't want to recognize him because he was the son of a brewer, but fortunately, someone we'll talk about next chapter, William Thompson, who was Lord Kelvin, up there, aristocracy, a lord, better than an earl, way up there, but also an excellent scientist. That didn't happen very often either. He took sort of Joule under his wing, and he saw what magnificent work he did and got him recognized. He became a member of the Royal Society and all that kind of stuff. Interesting character, a precise measurer, and he came up with many, many great improvements. Now, there's a good blurb here. Remember, this cannot be your source for your paper topic. This can be the source for your idea, but you'll need to go and find an outside source. The book is not your source for your paper topic. But he is there. And by the way, if you just read this, you'll run into other people like Lord Kelvin, who's William Thompson. Let's see. Thought there were some others here. But there's a lot of different topics here that you might hit on as well. And then there's a concept supplied at the bottom of that page on comparing amounts of energy sources needed to produce electric power. Generally 1 megawatt, which is 1 million watts, will supply the electric needs of 1,000 people. Okay? And then they have a little example here, and it's pretty interesting to work through. So I'll let you decide how much or little of that you're going to do. Then on page 78, the next page, wherever that is in your book, myths, mistakes, and misunderstandings, recycle or reuse. And he says here, it's a mistake to say you're recycling plastic bags if you take them back to the store when you shop. That's reusing, not recycling. It's good to do, by all means, but it's not recycling. Recycling means that the item is broken down into raw materials made back into new items. Okay? That's recycling. So it's not a major point, but it's a little minor point there. I think that catches us up to where we left off last time. Any questions? All right. We're on page, or in the new book, page 79, and talking about the different forms of energy. And the next of these, we talked about several, geothermal energy, and we just were beginning to hit on this when we ran out of time last time. Geothermal energy could be many things. Here they're talking mostly about heat from the earth. In a sense, wind energy is geothermal. Well, we've hit that somewhere else. This is the earth's heat from the earth. That's what thermal means, heat, geo means earth. Okay, heat from the earth. Several sources for this. One source is hot, dry rock. Okay? Of geothermal energy, this is about 85% of it. Now, it's not a huge percent overall, but of the geothermal energy we currently are tracking is off of hot, dry rock. This is in the U.S. anyway. It's almost always, I would say always associated with volcanic activity. So basically you have to have a near active volcano close by to be able to benefit much from hot, dry rock. Okay, and those aren't usually the best things to be living next door, okay, because they could go at any time. But there are several areas in the U.S. that do have this, okay, specifically the Pacific Northwest. Oregon is where Mount St. Helens erupted. Let's see, would y'all have been born then? Y'all remember that at all? Okay, probably not, sorry. Mount Shasta, Mount Rainier, all those are, well, St. Helens was recently somewhat active, but all the rest of them are not active, currently active. So you might have to go down a ways before you can find the hot, dry rock. But in the Pacific Northwest, I think it's a set of laboratories called Battelle Lab, and they have done a lot of, I think that's the name of it, they actually produce a fair amount of their electricity from exposing water to that hot, dry rock, heating it up, making steam, turning the turbines with that. No fossil fuels involved, no nuclear power involved, nothing except using the hot rock that are already there. Now, I mentioned last time, I think only one of you were here last time, that the country of Iceland takes big advantage of this. I would say a large quantity of their energy comes from hot, dry rock. Of course, Iceland is a volcanic island. It's on the mid-Atlantic ridge where the plates are separating and it comes out. In fact, not too many years ago, Iceland had such a major volcanic eruption that they had to close down Heathrow Airport in London because too much volcanic ash was heading that way from Iceland, and that's not a short distance, by the way. So those kind of places take great advantage of this. Iceland, I think, provides most of the heat for their homes, and guess what? With a name like Iceland, they're cold. They're really cold, and yet just about all their homes are heated from hot water coming off of volcanic rock. So they don't have to pay any electric bill, basically. They run a pump, I guess, just to pump the hot water through, and maybe that's even provided. I don't know. So, a great source when you can access it. Here in the eastern part of the U.S., I don't know of any active volcanoes at all. That would be mostly in Alaska would have some, and some of the other west coast. But, Hawaii would have some. Certainly, it's a volcanic island as well. All right, so that's one, hot, dry rock. Geopressurized resources, okay? This is like underground reserves of hot water containing natural gas, okay? They extract the natural gas from that hot water. This is about 14% of available resource. Now, they can use the heat from the water for some extent, but mostly they're capturing that natural gas. This is 85%, that's 14%. That's almost all the rest of it. Okay, but see, natural gas, again, is a fossil fuel, okay? It just comes up with the hot water, so they don't have to do as much drilling and that kind of stuff. And then dry steam, okay? Only 3 sites in the U.S. do you have this dry steam coming out of the ground. When they have it, use it. I mean, this is very good, cheap, but in some sense, the steam coming out of the ground it can be very dangerous. So you have to have some safety with it, but still very good. But only 3 sites in the U.S. I'm wondering if some of those are in Hawaii. I'm not sure for certain. And I wouldn't be surprised if some of them might be around Yellowstone National Park, because that's where a whole lot of geological sites are. Okay. Now, hot water makes up most of the recoverable geothermal resources. Okay? Like I said for Iceland, can be circulated directly into homes, businesses, farms, and so on. Use the heat and the energy that way. Now, this is especially true okay. It is close to how many use? That's right. Close to how many use that my work study student didn't quite get that right. I put it on the board before. All right, Siegfried's here. And we just increased the class size by another 20%. Okay, good deal.
I'm sorry, I was assuming that some of the people still in the teacher meeting over there.
Oh, they are still there, but
yeah.
I left early. I thought I said I'd gotten permission to leave early. Okay. So hot water, great recoverable geothermal resource. And again, it's sort of like this, just running the hot water over the hot, or water over the hot rock and using it for this. The trouble is, a lot of these places, you don't have a lot of population around. Like Yellowstone National Park in the corner of Wyoming and Montana and stuff, there are just not many people living there, okay? So not many people can take advantage of that. Where there are volcanoes near population areas, then they can take a bit more, okay? So, is it worthwhile to drill down to go deep enough into the earth until you start hitting the hot rock? See, for us, you would probably have to drill, I don't know, I would almost say a mile or so down. That's just cost prohibitive to get to any hot rock. Where there's volcanoes nearby, you don't have to go as far. But then most people don't live near active volcanoes, so there's a sort of a catch-22 there. Now, we mentioned this last time too, hydrogen. Anyone remember what we said about hydrogen? It is a very explosive gas, okay? So it burns very, very easily. That's why you don't see much hydrogen around, because most of it doesn't exist as natural hydrogen. It's already combined with something else. In fact, where's most of the hydrogen on the planet? What's it combined with? With water. It's in water, H2O. So guess what? That's not available hydrogen to be burning. Okay? But you have other issues. Even if you had much hydrogen, and when people do extract it, you have to store it somehow. And storing hydrogen, it's the lightest gas there is. It would take up enormous volume to capture much hydrogen, so most of the time they compress it. But when you compress it, it's under a lot of pressure. That could lead to leaks. If you had leaks, it could explode on you, okay? Not good. How do you transport it, okay? The easiest way to compress it is also to chill it, okay, and compress it. But then that takes energy to cool it that much, okay? So, and generally, like I said, not much of it exists as hydrogen, so you have to generate it in order to use it. Well, when you generate it, you're using energy to manufacture it. So you're not getting much energy out of it, okay? Now, they say one possible source, water, but in order to get this hydrogen free from the oxygen, you have to use a process they call electrolysis, which takes just as much energy to separate the hydrogen as it's going to take when you burn it, as you're going to get out of it when you burn it back with oxygen again. So what's the takeaway from that? Not much, okay? Now, they have developed some techniques whereby they do a chemical process that releases small amount of hydrogen fairly cheaply without using electrolysis, and then use it right away, so you don't have to store it and transport it and pressurize it and that kind of stuff. Those are still on the drawing table, you might say. People have got them working, but it's just not on a very large scale. Now, what's the advantages of hydrogen? What happens when you burn hydrogen? What's your waste product? Water, okay? Hydrogen oxide is water, okay? Can you get any cleaner than that, okay? No negative side to the waste product. Combustion produces water. Possible problems: it's best stored as a liquid because it takes up a lot less volume then, but in order to get it to a liquid, when they say cold, they mean very cold. Hydrogen liquefies at something like negative 250 degrees Celsius, negative 400 and some degrees Fahrenheit. That is cold. That is really, really cold. Okay? So they usually compress it, but when you compress it, it tends to heat up, so then you have to chill it more. But when you compress it, then it tends to leak easily because it's such a lightweight gas, and then it can be extremely flammable if you had a leak. So hydrogen cars are a great idea, except the tank to hold the hydrogen weighs so much more than the hydrogen does. So most of your weight is in the tank, not in the fuel, and then controlling it. Now I think here at Lawson State, the automotive program had a test run of using some of the electricity produced in cars to hydrolyze the water so then you could burn the water later. They ran that for a while. It's in the renewable energy section. Who did you say your instructor was? Willie who? Library. Okay. If it wasn't him, it was someone else who was hired about that same time who was running that program, I thought, at one time. Now he's with GM. So you might check and see. There was a prototype. I think Mr. Harris was involved with it some in the Ford program. They were trying a lot of different things to see if they could get some ways to work. So in many ways, we were pretty close to some of the cool stuff they were trying to do with that. Again, I don't know how successful they were, but it was really neat that we were attempting. Okay? Any questions on hydrogen? Okay. That is the last slide of the chapter. And I say this every chapter, and I'll continue saying it every chapter. Please read the chapters, okay? I can't possibly go over everything that's in the text in class. The slideshow doesn't show everything in the text, okay? Please read the chapter. Now, after you've read the chapter, afterwards, the summary is just that. It summarizes it. This is a really short summary here. You can't get off the whole breadth of the chapter in just this short summary. Now, the last chapter had something like 11 or 12 equations. This one has 5, but they're all really important key equations. Most chapters have a few more key terms than this one, but this one has several. They list them alphabetically, but they list the page numbers where you can find their first either mentioned or defined or whatever. But then the applying the concepts. And again, most chapters have more questions. This has 36. So most chapters are closer to 40 or even more than 40. So this doesn't have as many as most, but there's still great questions. If you know them, there's a good chance you're not going to have any problem on the test. And again, your test, just like the last one y'all did and the one you're doing now, Nick's doing now, is majority multiple choice. On that one, there's 3 problems that you actually calculate. One on the first page, one near the top of the second page, one at the bottom of the second page, okay? There may be a few fill in the blank. I don't remember. It seems like there maybe is on this one. But most of the questions are multiple choice. They won't be the same questions, but they'll be based on the same material that these are. Then there's also 12 questions for thought, which are, that's probably as many or maybe a few more than normal, and 9 for further analysis, okay? So those 21 questions are well worth you looking at. And then if you've got the full text, well, whichever text you have, there's parallel exercises on page 84, Group A and Group B. If you do one, they're very similar to the other. The difference is the Group A, if you have the big books, they have answers in the back. The little book, for some reason, they didn't print the answers in the back, so that you can get with someone who has them. Those are well worth a study. All right. Any questions? Chapter 3. So again, on today, the last 2 hours today, 5:45 to 7:45, they're not going to take you that long, we will have the last lab on Chapter 3. Okay? We're going to start Chapter 4 right away and get going in that and have 2 hours of Chapter 4 on Tuesday. Then, at 5:15, we will start the lab on the first lab in Chapter 4. And then at 7:15, or earlier. If you finish the lab early, which you probably will, you can start your test, and the test on Chapter 3 will be the last 30 minutes, or however long it takes. So any questions? That test is coming up Tuesday. Along with the first lab in Chapter 4, we'll do the last lab in Chapter 3 today. So let's get out of that and go to Chapter 4. Now, Chapter 3 was energy in general. Chapter 4 are 2 other manifestations of energy. Okay? So these two chapters really tie together fairly well. Most of what we studied about in chapter 3 was mechanical energy. Okay? What we're going to hit in chapter 4 is closer to what we call thermal energy. And it seems like it's taking a long time for it to load this. I don't know why. Let me try it one more time. It's sitting there shivering like it's trying to load, but it's not doing very much. Let me try it again. Okay.
I'm kind of like it's loading. Just a few questions.
Okay.
The formula we used in chapter 3.
Uh-huh. The summary of equations are on page 81, so that lists all of them. Does that include the one you're talking about? Yeah. Well, I don't know. It may be different in your book. It's at the right after the summary and 82. Okay. Is the equation you're talking about there?
That's it.
You got it? Is that what you needed? Was that all you needed?
Yes, sir.
Okay.
I thought you was waiting on that. Your thing to download.
Well, I am. So if you got a question, go on. Let's see. I got to do something different. It's not doing anything. Let me try this. Sometimes all you have to do is shake its cage a little bit. Here we go. Let me try it again now. All right, I don't know what's the problem here. The system gave me some problems this morning, but it wasn't this problem.
Now I logged on to it. This not affecting yours.
No, it should not. Okay. See, it seems to be stuck there. So let me try this again. Oh, wait. It just started doing something. Go back. There, no. Okay. I may come back and do it again, but let's see if something, it seemed like it did something different here. No. What I'm going to do is end this task and try it again. Okay. Now let's try it one more time. This time it acts like it's really going to do something. Let's see if it does. Yes, there it is. Now, I don't know why, but this is the one chapter that the other chapters are basically been black or blue or red print on the white background. This is white print on a brown background. So I'll use a different colored pen when we're solving problems on it. But this is just, they're different slides. Whoever did this had a different approach, okay? So we'll go from the current slide. And this chapter is talking about, like I said, thermal energy, which they don't call it that. They call it heat and temperature. All right? Now, the trouble is, or it's not really a trouble, it's just how we're going to approach it. We're probably going to start with the temperature end and move toward the heat end, okay? But we're going to talk about them both as we go, okay? So here's the core concept. It's kind of innocuous seeming. A relationship exists between heat, temperature, and the motion and position of molecules. Okay? Rather a vague sentence there. It doesn't really say a lot to me. But here's what they're talking about. Is heat the same as temperature? No, they're related, but it's not the same. Okay? So we'll talk about the differences between heat and temperature and heat and other things as well. We've already talked about the energy of motion and the energy of position. What were we talking about with them? Chapter 3. Energy of motion, energy of position.
That's the question again.
What were in chapter 3 when we mentioned the energy of motion? What were we talking about? The K energy, kinetic energy. Energy of position was similar. The P energy, potential energy. Okay, specifically gravitational potential, but other potential. Is that what we're talking about here? Well, kinda. Except it's not of the object, it's of molecules. Molecules are on the microscopic level. I mean submicroscopic level. Even with the strongest microscope in the world, you're not going to see many molecules. They're way too tiny even for that. So we're talking about kinetic energy of molecules, but also potential energy of molecules. So it's not the same kinetic and potential energy, though it has the same formulas and stuff, but we're talking about much, much, much smaller things. So heat and temperature are what we call macroscopic entities. Motion and position of molecules, microscopic or submicroscopic. So that's what we're going. We're going to be making connections between what's happening on the big scale, the scale we see, measure, deal with every day, and on the submicroscopic scale that you can't see, you can't feel, you can't sense, but you know the results of it. So here's the overview. Now, again, this isn't necessarily the order we're going to do it, but this is what we're going to cover. The concept of thermodynamics. What does the prefix thermo indicate to you? Heat, exactly. Dynamics is changing. Okay? So this is the changing of heat, the exchange of heat. And what we're going to do for thermodynamics, or what thermodynamics is the study of these macroscopic, the big scale processes involving heat, mechanical, and other forms of energy. Okay? These are things we see, we sense, we measure, we feel, that kind of stuff. Macroscopic. Okay? We'll look at some applications of this. Actually, most of this is toward the end of the chapter. Systems of energy inputs and outputs. For instance, heat engines. Can any of you think of a heat engine that you work on every day? Automobiles, exactly. Okay. How about heat pumps? Air conditioning, refrigeration is a type of heat pump, right? Okay. And refrigeration, the same thing. Now, all this stuff in thermodynamics is mostly based upon, but not concerned with, the microscopic details. We will deal with that first. So the approach we're going to take is discuss the underlying microscopic processes first. We will relate the microscopic and macroscopic all the way, and then we'll study the law of thermodynamics last, which are mostly macroscopic. Okay? So we're kind of turning it on its ear, on its head, or somewhere here, and that will be our approach. So let's start with the microscopic. Molecular. Kinetic meaning moving. The energy of motion of the molecules. The kinetic molecular theory. Now this is a whole bunch of different hypotheses about the particular nature of matter and matter surrounding space. Now if you go way back in history, this is actually before Aristotle, but it's still in the Greek time, they were the earliest to write up some ideals on atoms. Okay? Now obviously they didn't have the technology back then to actually measure atoms or really talk about it, but they thought about them. And the first of these was a guy named Democritus, okay, or at least the first one I've read about. He came probably a generation or two before Aristotle. And he just had this thought. This is what the Greeks said. They thought about things. They were great thinkers, by the way. But he said, let's just imagine we have a rod of iron here, okay? And let's break that rod into two, okay? Well, once you have two, then let's break the smaller piece into two more. And take the smaller piece there and break it into again. And how long can you do this? Keep breaking down that iron into smaller and smaller and smaller entities. His question, his thought was, do you ever reach the point when you have the smallest piece of iron that you can possibly have? And it makes sense. And he said yes. And he called that an atom. I don't know if he used iron, but an atom. An atom means indivisible. Well, we know today you can divide some atoms, okay? But back then that was his concept, and that's what an atom was named for, okay? Now, currently we know a bit more about this. And by the way, within a couple generations, Aristotle came along. He said, no, I don't buy this thing of Democritus about being a smaller thing. We think all matter is a continuum. You never can get to the smallest piece. You could always keep breaking smaller. Full of it, Aristotle. No, okay. But anyway, no one could prove it back then anyway. They didn't make a practice of doing it. So the current view is that matter is composed of microscopic particles called atoms. I'm going to say submicroscopic particles. Incredibly tiny little particles called atoms, the smallest building blocks of nature. The atoms combine to form molecules. We just had one on the screen just a little bit while ago. We were talking about burning hydrogen. What was the molecule we talked about? Water, exactly. H2O. Two hydrogen atoms, one hydrogen atom, make a water atom, okay? A water molecule, okay? So atoms combine to form molecules. And many of the macroscopic, that's big scale phenomena, can be traced to the interactions down on the microscopic and submicroscopic level. Okay, a lot of blah, blah, blah wording here, but this is indeed the way the thought process is going with this. Okay? Now, let's look at those entities we call molecules. Let's back up and first type with atoms. Talk about atoms. The smallest individual, unique particle of any of your elements, the chemical elements. And by the way, there are not that many chemical elements. Something on the order of 100, and the reason I say that so vaguely, in your periodic table in your book, this will be in chapter 8, that is in your book, all your books, you'll find this. If you got the big book, it's on the back inside cover. This goes up to 118, actually. But if you look at those bigger numbers, let me see if I can read some of them. Unum noctium, uniseptium, livermonium, unipentium. You know what those are saying? I think that's UN. I think that means unknown. Okay, I'm not sure, but I think it is. And one of them's the 8th, one of them's the 7th, one of them's the 5th, one of them's they're just named something because they really, theoretically they exist. I'm not sure they've ever actually detected it, or if they have, they don't hang around long because they're highly radioactive. They can't study them. They're just here and gone in less than an instant, okay? So for a bunch of those at the end, basically, in fact, all those who have parentheses around the numbers, the atomic masses, that means they're radioactive. They don't hang around long, not long at all. Before you get the last one that's not radioactive, goodness gracious, where is it? It's uranium, I think. And that's number 92. So from 92 to 118, just about every one of those is fleeting. They're not around very long. So they're just sort of theoretical elements, okay? They aren't something that you really have to deal with very much. Okay, so that's why I say there's around 100 elements. Chemical elements. They're defined by each unique type of atom. Every uranium particle is made up of uranium atoms. Every hydrogen entity is made up strictly of hydrogen. Oxygen is made up of oxygen. Every element is defined by a unique type of atom. Okay? And the whole study, when we get to chapter 8, we'll talk about that. But then you take different elements, like hydrogen and oxygen, burn those, and you get water. Okay? Or nitrogen and hydrogen, you get ammonia, or whatever, carbon dioxide, which is itself a compound, combined with water, which is a compound, and you get simple sugar. So yeah, compounds are pure substances, but they're made up of two or more atoms chemically bonded. Now that's the key here, chemically bonded. We'll talk about this more in chapter 8. Okay, if they're chemically bonded, that means they don't come apart. Now here's the other thing it means. It means that things are changed big time. For instance, let's take hydrogen. What do we say about hydrogen? Name a few characteristics of hydrogen. We mentioned several already. It's what? It's extremely flammable. It'll blow up. It's explosive. Very, very flammable.
One compresses H2O. One compress.
Okay, when you compress it, it becomes maybe a liquid and stuff. So normally it's a gas. In fact, it's the lightest gas we have. Okay? Extremely flammable. What can you tell me about oxygen? Say again? It's what?
I don't know.
Okay. It is the one substance, or there may be some others, but the main substance that's used to burn anything. You can't burn anything hardly without oxygen. Okay? It's essential for combustion. It's what you use in your cars. Okay? All that gas that comes in, nitrogen and everything else, only the oxygen is what really burns. Okay? So it's the one material necessary for combustion. So here you have hydrogen, an explosive gas, with another gas, which is oxygen, which is essential for combustion or burning. And when you combine those two together chemically, are they changed? You better believe it. Those two are gases. What is H2O? Water, which is a liquid at normal temperatures and pressures. You get a little cooler, it becomes a solid. You heat it up some, it'll go back to being a gas. It's a very different gas from the other two. What's one of the major things we use water for? The firemen? Put out fire. So here you have an explosive gas combining with the oxidation product that you need to burn things. And when they go together chemically, is it combustible? No. Is it explosive? No. We use it to put out fires. Okay? It's changed completely when you have that chemical bonding. Here's another thing. What's one of your ingredients on your bag there? I'm guessing the second or third major ingredient there. Okay, pass the flour, pass the cheese product and whatever. What's the next thing? Salt! Exactly. Okay? Someone tell me what salt's made of. You found salt on there somewhere, didn't you?
Yeah.
Okay, absolutely. Huh? Third ingredient? I thought so. Down, yeah. Okay. Okay. Salt is made up of two atoms. One of those atoms is from the element sodium. Can anyone tell me anything about sodium? It's a soft metal. We wouldn't even count it as a metal, really, if you saw it. You never see it, by the way. You'll hardly ever see pure sodium, okay? If you see it, it's probably in a chemistry lab. And if it's in a chemistry lab, it's stored underneath oil. It'll be that soft material that's at the bottom of this with a bunch of oil on top. It's sitting at the bottom. The reason for that, if it was exposed to air, because all air has a trace amount of water in it, if sodium gets exposed to water, it explodes. I mean major explosion. So here is an explosive solid metal that we combine with chlorine. Does anyone know what chlorine is? What's that? Yes, it's a poisonous gas. It's a green poisonous gas. You combine this explosive soft metal with a green poisonous gas, and what do you get? Salt that we use to eat. What are you eating? I bet you it has salt on it. Pita chips. I bet you there's salt in there. So we're eating what was an explosive metal and a green poisonous gas, but when they combine chemically, changes everything. So that's second. Yes, and it tastes very good. It flavors food, it's a preservative, has none of the same characteristics of the atoms that make it up. Totally none. So, macroscopically, we have the elements made up of microscopically atoms, but then when you combine atoms together microscopically to make molecules, then you have compounds, macroscopic. So element and compounds are macroscopic concepts. Atoms and molecules are microscopic building blocks. Okay? So, the smallest unit, the molecule is the smallest unit retaining the properties of a compound, not of an element. Smallest particles of an element will be the atom. Smallest particles of a compound will be the molecules. There's only on the order of 100 elements. There are probably hundreds of thousands of compounds, okay? So, smallest unit retaining that would be the molecule. Microscopic or the macroscopic concept of a compound. Now, here's the shorthand. Molecules can stand for either atoms or molecules. Here's the deal, okay? Let's take carbon, for instance. Carbon, by itself, just pure carbon, elemental carbon, is just carbon, okay? Each atom is its own molecule, okay? Same thing for many of them. However, hydrogen, oxygen, those atoms don't hang around as individual atoms. Hydrogen almost always is H2. Two hydrogens married together. Two oxygen married together. Two fluorines married together. Two chlorines married together. Most of the gases are what they call diatomic. So a single oxygen atom would be an atom, but a single oxygen molecule would be O2. They're still only atoms, but they're tied together as O2. Now, there aren't that many things that do diatomic, but there are a few. So we'll call those molecules of hydrogen or oxygen, or we can call them atoms of it, but usually the atoms are existing molecules. All right, now let's look at some of the interactions that molecules have. Most of the time, molecules attract one another. The reason for that is because of those electrons, okay? Remember, even the atoms are made up of smaller molecules. We call them indivisible, but we can separate and break them into smaller things. What are the three major components of an atom? Protons, neutrons, and electrons. We'll talk about this mostly later. The protons and the neutrons live in the nucleus. Okay, the nucleus is that center part of the atom. Okay, what's this?
I said nucleus. Well, I told you that was the
What's
sound,
that?
but it's right. You were right.
What's that?
I said nucleus.
Nucleus, excellent. They live in the nucleus, okay? The nucleus is that center part, and you can't get any more crowded than the nucleus almost. I mean, it is incredibly dense, okay? And all your protons and all your neutrons live there. Now, what's the difference in a proton and a neutron? Yeah, a proton is positively charged, a neutron is? Neutral, no charge. Okay, so all these positive protons and neutral neutrons live extraordinarily close together in a nucleus. Now, flying around these nuclei are your electrons. Now, all the mass, just about all the mass of that whole atom is in that nucleus. 1/10,000th approximately of the mass of a proton or a neutron is going to be the mass of an electron. I mean, that's so tiny, it would be like taking a proton or a neutron, if it's made out of the right material, breaking it up into 10,000 little pieces. One of those would be equivalent to an electron. Now, you can't do it, but if you could, that would be it. So the electrons have almost no mass. They have a little bit, but not much. And they fly around and take up the whole volume of that atom. Where the nucleus has all the mass, and it takes up just this tiny, tiny little speck in the center, but all the mass is located there. Okay. Now, do you ever exchange protons, one atom to another atom? No, that would take a nuclear reaction. Okay, you don't want to do that. But electrons, they're flying out here on the boundaries. Yep, you can lose them, you can gain them. That's what's going on, and because of that loss and gain of electrons, that's where the attraction comes. If one thing is slightly positively charged, the other slightly negative, there they go. They're attracted to each other. Now, if two things are both slightly positive, they're going to repel each other. So most of your molecular interactions are usually attractive, causing materials to cling together. Have you ever taken the clothes out of the dryer and can hardly separate them? Okay? That's because some fabrics gain electrons, some fabrics lose electrons, and they stick together, and you have to literally peel them apart. They call it static cling, when you put them in place. That attractiveness is called cohesion. That's the attractive forces between light molecules. Now, some of the molecules that practice cohesion would be water. In fact, water, if you look at it, okay, it's H2O. If you look at hydrogen in the periodic table, mass of 1, lightest atom out there. Oxygen has a mass of 16, still one of the lightest. So together, 2 hydrogen, 1 oxygen is 18. You look at any other molecules that have a molecular weight as light as 18, they're going to be gases. But water's a liquid. Why is that? That's because of cohesion, the attractive forces. Now, here's the deal, okay? This is getting into Chapter 8 material a little bit more than now. But remember I said the electrons are flying around on the outside, right? Now, they actually exist in different levels or shells. There are a few that are really close to the nucleus, others that are further out, and others that are further out. The outermost shell of most shells of electrons, they like to have 8 electrons in it. So there's not just 8 electrons, 4 pairs of electrons. That's what the ideal is. Now, if you could picture in free space an atom, or a molecule, or anything else, atom, let's go with atoms, and figure out how to space 4 pairs of electrons around it. Basically, you're going to wind up with 1 up here, 1 here, 1 here, 1 there. Turn it any way, and it makes what we call a tetrahedron. It's like a little pyramid type thing, but any way you do it, that's how you separate 4 pairs. Okay. Now, oxygen wants to have those. It only has 6 electrons in its outer shell. A pair here and a pair there. These 2 are unpaired, okay? Occupying those other 2 places on that tetrahedron. So that's what attracts the hydrogen. Because hydrogen only has 1 electron, so it goes with this one and 1 goes with that one. Now, there's no place that you can put these 2 that are not going to be adjacent to each other, and these 2 that already have 2 electrons, they're not adjacent. They're adjacent to each other too. And what that does is make every water molecule a little magnet, because it has a positive end where the hydrogens are, a negative end where those pairs of electrons are. It's a dipole. Okay? We'll talk about those in Chapter 6, the next chapter we did. Okay? Because of that, water molecules If this hydrogen here sees another water molecule on the water molecule, sees another one, it's attracted to the oxygen in it. And they hang together really tight. They cohese together. Okay? This hydrogen and this pair finds it's a hydrogen. This finds a hydrogen. So you get all this cohesion, and water has this what we call surface tension. Do you remember back our very first lab when y'all were filling those containers with water that you're doing that experiment on ratios? Okay? And remember I kept saying, oh, add a little more. Add a little more. And what finally happened? The water was over the top, but not spilling. Remember? It actually pumped up on top. And that's because water molecules were hanging on to each other so tightly, they wouldn't let the drop off. You could add a little bit more and then it would spill. But up to that point, and here's the other thing. Have any of you ever been swimming? Okay? Ever jumped into the pool and done what they call a belly flop? Does it feel good? Not at all. Why? You're only hitting water. It's a liquid. But it has that surface tension. And boy, that's hard to break. In fact, if you watch the Olympics and those high divers, those going up, if you ever notice, the water was always being disturbed at the bottom. If that pool was perfectly flat, those guys diving from way, way up there, and gals too, if that water wasn't being disturbed, when they hit the water, they'd probably break fingers because the water surface tension is that strong. So they had pumps down there disturbing the water. Now, the other thing it does is make it easier for them to see. If that was perfectly flat, they would see reflection and wouldn't tell how close to the water they were. So there's two reasons they disturb the surface. But that's cohesion, the attractive forces between like molecules. Now, there's another kind of attractive force, and that's adhesion. Now, what does that almost read like? Adhesive, yeah, like an adhesive bandage or something like that. This is attractive forces between unlike molecules, like the glue on the envelope and the paper on the envelope. They adhere together, and you hardly can get them apart without tearing, okay? That's attractive forces between unlike molecules. That's what we get when water wets the skin. Now, I don't know if you've ever, some of you probably deal with oil somewhat, and if oil's on your skin and you go to wash it off, not easy to do, is it? Because the water just beads up. Because, you see, water and oil don't adhere at all. In fact, they are repulsive from each other. If you are trying to make your car or truck look really good, after you wash it, you wax it. And after you've waxed it, and it's out in that first rain, what happens to the water? It beats up and rolls off. It doesn't stick. Because water and wax, which is almost, as a hydrocarbon like oil, it doesn't. So it's not attractive. What's that? I can't hear you. Yeah. Rain-X? Oh, okay. And it keeps it from, does it? It'll beat up. Okay. I was wondering what it was. Because alcohol tends to make it wet better, but it's different from that. Yeah. Okay. So, yeah. So that's the same type of a deal there. Okay? But when they do attract, unlike particles, we call that adhesion, and that would be like water wetting the skin. And what helps water wet skin better? What helps water wet skin better? Yeah. Huh? Soap, exactly. Soap is actually what they call a surfactant. And what a surfactant does is break down that water tension between, say, oil and the water and stuff like this, and makes it wet better. Okay? But water wetting skin, that's adhesion. Your glue mechanism, that's adhesives. That's why they call them adhesives. Okay? But the interactions may not be attractive like cohesion between like molecules, adhesion between unlike molecules, they could be repulsive, and that would be water beating up on wax or the other substances you were naming. Okay? That is repulsive. Now, I think you may have also noted this in the lab. I don't know if you did. I didn't take time to talk about it. But when you were filling those graduated cylinders with water, okay, and reading how much water you had, I don't know if you noticed it, but the water tended to climb up the edge of the cylinder, and it was hard to read. Usually what we do is read the meniscus at the lowest point because it was bending it. That's because water adheres to the glass or to the plastic, depending on what kind of graduated cylinder you have. Now, in one of the next labs, in fact, not the lab we do today, but the lab we do Tuesday, we'll be measuring temperatures using thermometers. Now, there's two common materials that are in thermometers. Anyone know what they are? Mercury is one. And mercury, when you read that inside glass, your meniscus is like this. And you usually read the top of the meniscus. Because mercury repulses, doesn't like to touch the glass, and it gets as far away from it as it can, like getting like this and hanging at the top. Whereas the other, not mercury, but what is the other fluid in there? Heidi mentioned it earlier, alcohol, colored alcohol in thermometers. The red, that's usually alcohol. You'll see that meniscus tries to climb the sides. Mercury tries to get away from the sides, okay? Because alcohol is usually attractive to glass, whereas the mercury is repulsive to glass. So there's another example of different materials having different responses. Okay? Any questions on molecules? I'm not keeping up in the book. Let me make sure that I am hitting everything. Okay. Let's look at the phases of matter. Now, I don't know, I remember back when I was in school, high school and that stuff, we used to call these the states of matter. They've gotten away from calling them states because when quantum mechanics came along, they used the word state to mean something very different from phase. So now we call them phases of matter. What are the phases of matter? Solids, liquids, and gases. Has she got them all? No, there's one more. Second, solid, liquids, and gases. Okay?
Morpheus solid.
What's that?
Morpheus solid.
No, that's still either a solid or a liquid, one or the other. There's a few in this room that are neither solids, liquids, or gases. Don't look around down there. You won't see them there. Oh, what's in these tubes?
Fluorescent.
Yeah, it's a fluorescent light. What's in that? It's actually not a gas. It was a gas. It was mercury vapor. But what happens is the fluorescent lights have big ballast cells, like a huge capacitor. And it builds up a lot of charge and it charges that gas. That's the key. When a gas becomes charged, it becomes an ion, and the ion is called a plasma. So plasma is the fourth phase of matter. We don't usually think of that because we don't run into them every day. Okay? Which you think is the most common in the universe? Solids, liquids, gases?
Yes.
Gases?
I think liquid.
Liquids? Plasma! Guess what? She's right. Because guess where plasma lives? Not much on the Earth. Second? No, well, there may be some, but that's mostly liquids or solids. The sun is almost totally plasma. It's so hot, everything's ionized. Not everything, but most of it. And guess what? Most of the mass of the solar system is in the sun. Not on any of the planets, not even Jupiter. Compared to the sun, just a drop. So most of the stars, which is most of the mass of the universe, are plasma. Okay? But we don't live there. We live on Earth where everything's solid, liquid, and gases. And yeah, probably then, I would guess probably surface of the Earth, liquid, you're right there. But if you go very deep, there's always solid under there. But you go even deeper, it gets liquid again. So it's sort of hard to say. But I would say probably on Earth it would be more solids. Okay, but that was a trick question. Okay, as you would think. Okay, what makes a solid a solid? What's that? Very good. The atoms are tightly tied together. Okay, is that what you're trying to say? And not just in proximity, but in placement too. They're not just close together, but they're in fixed placements. Okay, that's what makes it a solid. Therefore, it has a definite shape, and because they're close together, it has a definite volume. Okay. Now, why is that? There is a rigid, most of the time, three-dimensional structure. For instance, we talked about that table salt. We're going to see a picture of it, in fact, maybe right now. Yeah, well, no, that's not it, but this is sort of the concept of it. That's a two-dimensional structure, but actually, put another one back here and one back here, you got three-dimensional. Okay. So, anyway, the rigid three-dimensional structure, the atoms and molecules are bonded in place. Not just in proximity, but in certain places. Okay? The allowed motions are restricted to vibrations in place, and that's all they can do. They can't spin, they can't do anything else, they just sit there and vibrate. And they do that, and we'll talk about that a little bit later too. Okay? That's what makes a solid a solid. Now, how do you take something that was a solid and make it a liquid? Let me see, are there any other slides here? No. Okay. How do you take what was a solid and make it a liquid? Typically. What do you do? Heat it up, exactly. Add heat to it. Okay? And what does adding heat to it do? Okay, you're very good. It doesn't really break down the molecules, but it breaks down that bond between the molecules. So this solid, they're held in place. Three-dimensional springs here. They can vibrate, but that's all. But you start adding heat, and you can break those bonds that hold them together, and now form a liquid. So you add energy or heat to a solid, and it becomes a liquid. It still has a definite volume because those liquid molecules stay close to each other, but indefinite shape because now they can slide past each other. They're not held in the same position. They're held close to each other, giving them a definite volume, but now the shape takes whatever the shape of the container. So what you have now is only weak cohesive bonds between the component molecules. In a solid, they were very strong cohesive bonds. But you've broken those bonds with the extra heat, making weaker cohesive bonds between the molecules. Still stay close, but they don't have a fixed position anymore. The constituent molecules are still in contact with each other, mostly. They stay close because they're attracted to each other. They have weak cohesion, but they slide past each other easily, and that's what loses the shape. So now what are the allowed motions? They can still vibrate just like they did before, but now they can rotate as well, and they can translate a little bit, move in straight lines. Okay? That's what makes a liquid a liquid. And here's their illustration of that. This is, say, a diatomic liquid. I can't think what one that would be. Most of the ones I know are triatomic, but anyway, they can vibrate between each other. They can rotate around each other. And they have a little capacity to translate together in some other dimension. Okay? So this is what goes on. But they stay close to each other. Really, really close. Okay? So they still are weakly attracted. But they're just not fixed in position. They can slide past each other really, really easily. All right. Trying to think of the best time to talk more about water. That's probably coming up later, so let's hang on. What do you do to change a liquid to a gas? Heat it up some more. Add more energy to it. And what are you doing now? Well, when you add more energy, let's go back here. Now you're separating this cohesive nature, and now every molecule is on its own. They go wherever they want to. If they ever collide, they don't ever stick. They just bounce off of each other and go on their merry way. Liquids, they stay close. Solids, they fix in place, okay? But gases, they just move around wherever. So what do? Add heat. Add energy. Indefinite volume, indefinite shape. Let's just say that I brought into class here a bottle of ammonia. Could use perfume, but I think ammonia is better. Pretty obnoxious stuff. What if I were to open that bottle? And I'll leave the room, okay? After a while, Nick's eyes are watering. He can't stand it, because those ammonia molecules, gas molecules, are entering the space, and they get him first, and then Emmanuel, and then make their way all the way back to Lacey after a while. After a while, everybody smells them, okay? But they're filling the entire room. Liquid won't do that. Open a bottle of liquid, it stays in the bottle, but the gas expands. Open a package of a solid, it stays right in place. It doesn't do anything. So indefinite volume and indefinite shape. The molecules are mostly not in contact with each other, and even when they are, they bounce off each other and don't stick together. The allowed motions, now they vibrate, just like before. They rotate, just like before. Molecules of more than one atom. Of course, it's hard for a single atom to rotate. How can you tell? And then the translate from one or random, mostly free paths, wherever they want to go. They hit the wall, they bounce off the wall. It's like the old game Pong. It hits the side and bounces off somewhere. They go wherever they want to. Okay? And they're showing this as a monatomic. They just are going everywhere. They're not staying close to each other. They're certainly not fixed in place. They're just filling the whole body. Okay? That's your gases. Now, they go right to something else. Before we do, let's talk about plasma. What do you think it takes to change a gas molecule to a particle of plasma? Called an ion, by the way. Add more energy to it. Absolutely. That's exactly what I described on here. That's not just heat, it's energy. This is electrical energy, energizing that, I think it's sodium vapor that's in there. Mercury, I call it before. Mercury vapor that's in there is what they used to use. I don't know if they still use it. They're trying to get away from mercury because it's such an environmental hazard. But whatever they're using nowadays, that's in there, that you add more energy to it, electrical energy. Now it becomes ionized. Now it goes flying down to the other end of the tube, back and forth like this. You see them when they start to go off. You see the waves sort of doing like that when the voltage is going about to end its lifetime there. You can sometimes see that in the tube. But what is happening is that energized ion, which is a gas molecule that's been energized, goes past that white powder that's inside? If you ever broken one, you know that white powder. That's a phosphorescent material, which means when certain things go by it, the electrons, everything depends on those electrons, jumps up an energy level. This is a quantum mechanics. Jumps up an energy level. Then when that energy goes past, it falls back down again. Well, when it falls down, it gives off a photon of light. And that's what we see. So that's going on all the time there. And that's why the fluorescent materials work. Okay? So that's what happens. You just do that. What's happening in a star? There is so much energy. It's mostly heat energy there. Boy, those things are at incredibly high temperatures, and that's why the light is being given off, heat's being given off, everything's being given off. So those are your phases of matter. That goes on page 87 and 88. Okay. Now, Now we're moving to molecular motions. Okay. So this is on the bottom of page 88. Molecular motions, they're characterized by, now if they're in motion, guess what kind of energy they have? They're in motion. Kinetic energy. And guess what? Every molecule is always in motion. They're so very tiny, but they're always moving. You never find one that's absolutely still. No such thing as a dead molecule. Okay? Always in motion. So they're characterized by an average kinetic energy over a large sample. Molecular motion. There could be some molecules in there that are moving 7 times faster than the others. They're all moving. Some are moving fast, some are moving slow. So what we do is the average kinetic energy of those over a large sample, and that's what produces what we call temperature. Temperature is the measure of the average kinetic energy of molecules making up the substance. Now you think of temperature as being a macroscopic measure of how hot or cold something is. You're absolutely right. But guess what? That depends on what's going on the molecular level, the microscopic level, and that's the average kinetic energy of those molecules. So the temperature is proportional to the average kinetic energy of the molecules. That is exactly what temperature is. Now, what is some evidence of that? All right, let's say I had my bottle of ammonia up over here in the corner. I just have opened it. Nick's eyes haven't begun to start watering yet. Okay, he hasn't got up to leave the room. But what if I put it on a Bunsen burner and start heating that ammonia gas? It's going to spread big time. So gases diffuse quicker at higher temperatures than they do at lower temperatures. And you know that's true. When I walk into the house tonight, almost every time the first words out of my mouth, especially when I get there about 8:45 or so, after teaching this class, first thing is, boy, something smells good. If Karen's been cooking something, that increased temperature gets those gases into the thing, and I can smell, boy, something smells good. And of course, I'm really hungry too. But gases do diffuse quicker at higher temperature. Now, another piece of evidence, okay? And guess what? This is true for solids, liquids, and gases, okay? What happens when you heat a piece of metal? Of course, it gets hot. But what else happens? Okay, it may change color. But what else happens? And it could melt when you got it hot enough. It expands, absolutely. Now, you don't see it expanding, but you know it does. How do you know? Have you ever heard a train running down the track? Surely you have. What noise does it make? Click, 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 click. Doesn't it make that kind of noise? Why? Because those tracks are made up, and it makes sense. All one can put down so much length of track at a time. So I don't know how long they are. Anyone know? They're really long, but they always have between those pieces of metal a gap. If you didn't have that gap down, and you put that down in the middle of wintertime, and you put them jam against each other, because I don't like to hear that click. Of course, everyone likes to hear the click. Guess what? Middle of summer, trains are going to be derailing because it's going to bend and warp. If you've ever seen a picture of where that's happened, it's unbelievable. That metal will bend like that. Now, have you ever noticed on your bridges, right, before you cross the bridge, what you notice? Boom, 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 going on and coming off. Why? There has to be an expansion joint there. The metal bridge is usually made out of metal, or at least metal has metal in it. They have to have room for that expansion. Nowadays, they do sort of a tongue and groove type thing. And when it's cold and contracting, you don't have as big a gap there because of the tongue. But when it's hot, they move right up really into each other, okay? And you can watch those. If you've got one near where you live, look at it sometime. In the coldest part of winter, look at the same one. Take a picture with your phone, you know. Take a picture of the coldest day of the year, take a picture of the warmest day, you'll see that metal has moved pretty significantly. Okay? Expansion and contraction with increasing or decreasing temperature. Does that happen in liquids? Oh, yes, yes. You heat a liquid, it's going to expand. You cool a liquid, it tends to contract. Okay? That's what thermometry is, isn't it? That mercury, when it gets warmer, it's expanding. When it's cooling, it gets smaller. That alcohol is going up or going down. If you had water in there, it would do the same thing. What's the problem with water? Yeah, it will freeze too quickly. Alcohol doesn't freeze easily, and mercury sure doesn't freeze easily. Okay? That's why they don't use water in thermometers. Okay? And that leads to something else, and I still don't know if I want to bring it up now. But anyway, does that work with gases too?
Not as fast as this.
Even faster. Huh?
Even faster.
Yeah, maybe it does. Okay? Didn't I tell y'all the story of shooting basketball with the kid that I used to do things with in Nebraska? I mean, I've told that story. There was a lady and her husband had divorced. She was raising 2 kids herself. Their young boy was in early high school, I think, something like that. And she said, you know, he really needs a male to be around some, you know, not just his friends, but, you know, a male role model figure or something like that. I was single, you know, in college, you know, grad school. I thought, not me. I don't know anything about being around kids, you know. I've had brothers and sisters. I didn't like them. No, I didn't say that, you know. But, so I thought, not me. But then he came out and played. He was a really good athlete. Played on our church softball league team. And I was not very good at it, but I was catcher, so I ran my mouth all the time, you know. And he was playing third base. He was really good. So I sort of started encouraging him because he was a good athlete, but he was really shy about being around all these men. And a lot of them were older than I was at the time. So I sort of, you know, encouraged them and stuff. And so we hit it off and became really pretty good friends. So I thought, okay, I'll start doing it. So I'd go over, say, on a Sunday afternoon. And Nebraska can get pretty cold. And one Saturday night, I think it was, he had left the basketball, or Friday night probably, had left the basketball outside. Forgot to put it up. Typical kid, right? And when we went over that Saturday morning, he wanted to shoot some baskets, couldn't find the ball, found it outside. So went to pick it up, and of course it felt like it was flat. Why? Well, he thought he had punctured it. He said, oh, I better blow this up. I said, well, no, don't bother yet. Why don't you put it in the house for a little while, and we'll do something else. He thought I was sort of nuts, I think. So anyway, we did something. I thought of something that would be fun for him to do, so we did. And then about an hour and a half later, I said, hey, how about going to get the basketball? You still want to? He said, yeah. He said, well, I just need to blow it up. I said, go get the basketball. He went and got it perfectly full. Why? Outside in the cold, and it was probably around 20 degrees outside then, that ball felt like it was flat because the gas had contracted. And when he took it inside, where it was probably 70 or so, it's tight as it could be, as he wanted it to be. So expansion, contraction. Yeah, gases actually do it better than liquids. Liquids expand and contract better than solids. Okay? All right. This is a representation of the numbers of molecules going at different speeds. This was an experiment, I think, first done by, I think, a French guy named Fizeau or something like that. He decided to heat this material. I'm guessing it was carbon, like soot, you know, heating that in a box, okay? And as it heated, it became aerosolized, you know, it became a gas, or went into the gas, okay? And then he had a bunch of what he called collimators that break down and made it all travel in the same direction, because all heated everywhere. But he collimated it, probably a series of plates and things to keep it in the column. And then there was this device he had here at the edge. And this device he could turn at a fixed rate of speed. It was a cylinder. But right down the cylinder was one solid track, right, fixed distance apart. And on the inside of that cylinder, he had a photographic cell, something taped on the inside that you could see those carbon atoms or counting, and so when it was turning, anywhere else, the carbon just went on the outside of the tube, didn't get to the inside. But when it hit that crack, all the carbon coming in right then went right through the seam. And then it kept turning and it cut it off. So it was like a real quick spurt that happened to be right outside then, and then it cut it off. Well, that spurt went across the interior of the cylinder, and some of it plated out on the back of the cylinder, and some of it plated off later. And anyway, as the cylinder turned, just a little bit plated off. The very highest speed stuff plated first, and then the bulk of it plated off next, and then a few stragglers plated off later. But he could guess, because he knew how far it was across there, how long it took it to move, he could come up with the speed of those molecules, or atoms if it was actually carbon. And this was his distribution. Increasing numbers this way, increasing speed this way, and this is what he got. Now, at a certain speed, he would get that just about every time. Until he turned up the heat on the source here. And when he did that, the curve went like that. And heated it more, and it went like that. It increased. The peak moved to faster speeds at higher and higher temperatures. And this is how he related temperature to average kinetic energy. Because speed is related to kinetic energy, and temperature is related to average. Kinetic energy is related to speed, and temperature is related to average kinetic energy. Really nifty experiment. One of the first ones that actually proved this relationship that we all assumed that got it down. Different from the Greeks, okay? Did a really nifty experiment there. All right. That's around page 88. Let's see. Before we go to temperature, there's a concept supplied at the top of page 89 or somewhere thereabout, depending on what book you have. Moving molecules. Blow up a small balloon, make a knot in the neck so it will not leak air. Notice the size of the balloon, then place it in the freezer part of the refrigerator for an hour. What you reckon it's going to be then?
Small.
A limp weenie, right? Very small. Take it out and let it warm up again. Goes back to being just about what it was before. Hold it over a pan of boiling water, but don't let the water hit it. And that thing will start expanding more. So you can do the same type of experiment there in your kitchen if you wanted to. All right? Not quite as specific as Fizu's experiment, but something pretty close. All right, let's talk about temperature. We defined it on the last slide that temperature was proportional to, it's a measure of the average kinetic energy of the molecules making up the substance, proportional to that average kinetic energy. So what is temperature? Simpler definition is a measure of the internal energy of the object. Internal energy being that average kinetic energy of that object. So how do we measure temperature? Thermo, heat, meters, measurers, thermometer, that's where that comes from. Heat measurers. But it's not really heat, it's temperature. There, got it a little off there. Used to measure temperature. In fact, the next lab we do, the one we do Tuesday, will be thermometry. Okay, we'll play around with a few thermometers. Now, how do thermometers measure temperature? Temperature is not something that, oh, I see how much the average kinetic energy of that thing is. Now, you don't have any device that does that, okay? So what do we use?
The gases.
Okay. Second?
The gases thermometer will expand and contract with the heat.
Okay. Actually, you're describing, guess who came up with the first working thermometer? Probably good old Galileo, okay? That first scientist that we had, you might say. And he used exactly what you did. He took Water, you know, I don't know if you've seen some of those beakers they use in the chemistry lab that have the long neck. Okay, put some water in that, okay, and then flip it over into a pan of water, and then as the air that was left trapped in the top heated, it pushed the water down into the pan, and as the air cooled, it sucked up more water because, just like you said, air expanding and contracting. Of course, the scale was sort of upside down. The higher temperatures were down here, lower temperatures up here, but that's how he did. There was one problem with that thermometer, though, one major one. It didn't just measure temperature. What do we use a device that almost looks like what I just described there? Barometer. Yes, it's measuring barometric pressure as well. So if you had a high pressure system come over, then it would push the water up without a change of temperature, and this thermometer would indicate it's at a lower temperature. Or if a low pressure came out, then the water would be pulled down and it would be a different reading at the same temperature. So that was the problem, that he couldn't distinguish barometric change from temperature change. Guess who improved on that? Who followed Galileo? Newton, exactly. Newton came along and said, oh, well, let's just take the pool of water out of the picture and let's put the liquid in a tube, seal the tube, and then let it expand and contract. Not the gas, but the liquid. And so good old Galileo came up with some good ideas, and Newton came up and made them better, okay, just like they did with the laws of motion. Okay, so that's one way. Expansion of a liquid, expansion of a gas. Would expansion of solids work?
I believe it does.
Believe it does.
Glass.
Yeah. Say again?
Glass.
Glass?
Doesn't it expand and contract?
Okay, it does a little bit. You're absolutely right, but it's hard to measure that. But what they do, and let's see if they got a, yeah, here it is. Bimetallic strips and thermostats. Let's see if the picture is that. I think the picture is something else to begin with. Yep, nope, there it is. Bimetallic strip. Okay, what they do here, because solids expand and contract so small, really has to have a very sensitive needle and very small scale magnifying glass to see what those changes are. So what they do, they put two different metals, like iron on top and brass on the bottom, and put them in one strip. And then, because iron doesn't contract and expand as fast as brass does, when the brass expands, it pushes the iron up. And you can put a needle on this. There's the temperature. Okay. There was the room temperature, and then it went up to 150 degrees or something like that. Much easier, much bigger. Okay, but it still doesn't really do that much. So what they do, they wrap this around in a coil. Have you ever looked inside an old thermostat? That coil of metal that's in there? Bimetallic strip. So now you've got a really long piece of metal, but it's round and round and thing. So when it does, it has even more effect. So that coil in a bimetallic strip in thermostat. Now this is a fairly new thermostat. I bet you it doesn't have it in. But we had one down in the lab, 259, in one of the drawers. I don't know if it's still there. If we go down there, we'll try to remember to look at it. Okay? But what you measure is not temperature. You measure surrogate properties like expansion and contraction. Okay? In your car engine, what is reading the temperature of your engine, is it that measuring the temperature of the water in your cooling system? Is it that really what it's measuring? What is that? Do you know? It's a what?
Coolant temp sensor. Coolant temp sensor.
Cooling temp? Is that
Coolant temp.
Okay.
Yeah. Radiator, water, coolant.
Okay. I can't quite understand the word you're saying.
Coolant.
Coolant?
Yeah. It's what cools it down.
Yeah.
The water coolant in the radiator.
Right.
It measures how hot that is and then
Right.
measures how hot it is.
So what is it actually measuring? Do you know?
The resistance.
Okay, I thought that was it. It's called a thermistor. Now you're measuring temperature with a resistor. Okay? Because when we get to the electric chapter, we'll learn this too, that when temperature goes up, the resistance goes up. When temperature decreases, the resistance usually decreases. So you're actually measuring with an ohm meter. It has nothing to do directly with temperature, but as you're measuring the change of resistance in an electrical conductor. It's called a thermistor. I was hoping that's what it was. I thought it was. There's also things called thermocouples that are sometimes used to measure temperature. Those are measure electric conductivity as opposed to resistance, okay, which is almost the same type of thing. So there's all sorts of different ways to measure. What you measure are the thermometric properties or changes, they're surrogates. You're measuring something else, but letting that tell you what temperature it is. Okay, good deal. I don't know what slide was there. It may be the picture on page 89 of that bimetallic strip in the thermostat. I can't see it because it's not showing up here. So now let's talk about the temperature scales. Okay? Who, as I said, came up with the first thermometer? Galileo. Okay? Improved on by Newton. And I believe, if I'm not mistaken, Newton just sort of arbitrarily said, let's just take between the freezing point of water, water being the most common substance on the planet, very available, freezing point of water and the boiling point of water, let's just say that's 12 degrees, okay? So he used the 12-degree scale, okay? As people started measuring things more and more precisely, they started breaking that into half degrees, and then quarter degrees, and finally into eighth of degrees, okay? And they didn't like messing around with fractions, unlike you. I know y'all like fractions, okay? So they said, let's not use 12 degrees, let's take eighths of those 12 degrees. Well, what's 8 times 12?
That's 96.
96.
Yes, sir.
Okay. And I'm sorry, maybe I got that wrong, because I think that might be body temperature you had at the end. That's what it was. It was body temperature. So if you did, rather than calling a degree the 12th, break that into eighths, now you got 93 degrees from the boiling point. No, that wasn't right. No, it's a boiling point, right, to 96. Well, later they changed that to 100, just to round it up. So it was 96, but it really didn't work well, so they moved it on up to 100. But it's the fine, and WRT means with relation to, okay, various reference points. Well, along came another guy. He didn't like using water as his zero for the boiling, freezing point, and now they did 100 for the, 96, say, or 12, or whatever. For the Fahrenheit came along, he said, no, in my labs, we get things a lot colder than that. Now, how did he get things colder than the freezing point of water? Okay? He didn't have that much to do. Have you ever, in the summertime, decided to make homemade ice cream?
Yes.
How do you do that?
Salt.
You salt the water, the ice,
Yes.
right? What does that do for you?
It
It lowers the freezing point of water, which also lowers the freezing point of the milk and cream and stuff that's inside. Because if you just used ice and did it, you could crank all day long. You might make butter after a while, but you're never going to make any ice cream. Because most of ice cream is water. I mean, milk is mostly water, but it has cream. That's what I call ice cream. Emulsed in it. You have sugars. You put a little sugar in it, you put fruit in it, whatever you put in it. All that basically is dropping the freezing point of the water. So you have to do something to ice to drop it even more, and that's what Fahrenheit did. He was adding salt to his ice and dropping the freezing point. Well, on Newton's scale, that would have to be a negative temperature. Okay? Well, negative temperatures are hard to mess with. He didn't want to mess around with negatives. Y'all like negatives, but he didn't. Okay? So he didn't want it. So he said, let's get a scale down as cold as I can go in my lab. Okay? And that wound up being his 0. Okay? Which moved the freezing point of water up to around, on the Fahrenheit scale, 32 degrees Fahrenheit. Okay? But he wanted to use body temperature as 100 degrees. Well, it wasn't exactly right, but close to it. Well, then what would that put the boiling point at? 212 degrees Fahrenheit. That's the boiling point of water. So, strange scale, but he did it. Fahrenheit went from 0 to 32, 32 to 212, or close to 100 for body temperature, and then 212 for boiling point of water. Okay? Well, guess what? In no time, they started using different materials and compression and expansion and stuff, and they could get much colder than Fahrenheit. And that was just how much salt, it was a very difficult thing to do. Under Celsius, by the way, that was Gabriel Fahrenheit. By the way, these are all potential paper topics. Remember we talked about those. Y'all were wanting to find some paper topics. Who was Fahrenheit? How did he develop the Fahrenheit scale? Who was under Celsius? How did he develop that? Why did he develop that? Who was Fred Kelvin? I don't know. That wasn't his name. What?
I got a question.
What's that?
Sort of deal with this, but what is absolute 0?
Okay, we're getting there. Good question. You're anticipating really well. That's the Kelvin scale. The absolute 0, that's what the Kelvin scale is based on. Okay? But we're coming up to that really shortly. So can you hang on a minute and we'll get to it. Okay, Celsius went back to, look, how much salt Fahrenheit puts in his lab? That's not good. Let's go back to something, and he put 0 at the freezing point of water and 100 at the boiling point of water. And originally they called that the centigrade scale. Centi meaning 100. 100 degrees between freezing point and boiling point of water. Well, after a while, they didn't want to call it that. It may have been after he died. They said he came up with this, let's name it after him. They still called it capital C, but now it was Celsius. Okay, an excellent question on Kelvin. Who was Fred Kelvin anyway? There was no one named Fred Kelvin. Remember I mentioned him before? William Thomson. But why did they get Kelvin? Where did that come from? Lord Kelvin. That was his title, was Kelvin. Not his name, but it's still capitalized because it was named as the thing. Lord Kelvin. Okay. Now, the book doesn't, maybe the book does it, but the slide set doesn't do it. Let me give you a quick and dirty on basically how Kelvin and others came up with the absolute 0 scale, okay? Or used absolute 0. What they did, and I'm going to get a color. I'm not sure we have white. How about the yellow? Yellow will do? Okay. What they did, they had scale here. What they had is different gases, okay? Had to be using gases. And when they had this certain gas at a certain temperature, you can pick a temperature, whatever it was, there was the volume of that. Here was the volume, here was the temperature, okay? And you cool the gas, and guess what? The volume decreases, and cools some more, and cools some more, cools some more, cools some more, cools some more. And this is almost a straight line. I'm not drawing it very straight. Cool some more. Now, what happens to a gas if you keep cooling it? Ultimately, it suddenly become a liquid and just almost go to no volume, okay? But the linear pattern was here. It's heading somewhere. We'll take a different gas, and it might be here, and here, here, and here, and here, and here. Now, it may go to the liquid, but if you extend that, hey, going to the same place. Take a different gas, and it might be here, and here, here, there, 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 and then it goes to liquid. But if you extended that, extrapolated it, they all wound up the same place. Now, what did that stand for? That appeared to be Lakeisha, okay? Oh, I'm not, okay. She's here, okay? What it's been, now look at what we're saying here. The volume apparently is going to zero. Now, do you think the volume ever really goes to zero? Not quite. But where it seems to go to zero, that would mean, and what is it keeping it from going to zero? The motion of the molecules. That's why it keeps it in a bigger space. Because when you decrease the temperature, they move more slowly, the volume decreases, just like that basketball, remember? So if you continued out here, this is where they would say it would go if it got as cold as it could possibly get. On this scale, you can't go any colder because the volume can't get less than zero, okay? So this they call is absolute zero. Every temperature you measure is going to be zero or positive, okay? Now later we're going to talk about the 3 laws of thermodynamics. The third law that we really aren't going to talk about much is this. You can approach the absolute zero, but you can never reach there. That's the third law of thermodynamics. We won't go there yet, and we won't get into a why, but that's indeed it. But basically it's saying you can almost get down to zero, but you can never reach it, so therefore every temperature you ever measure is positive, like an absolute value. That's why they call it absolute zero. That's as cold as anything can ever go. Okay? Now, in deep, 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 deep outer space, you're approaching absolute zero. Okay? Because there's no heat source anywhere, but it never can get any colder than that, because that's as cold as anything can go. Now, in the old days, they said that's when all motion stops, therefore your volume goes to zero. Nowadays, with quantum mechanics, they say, no, that's when things go to the lowest energy state possible. Motion never stops. But at the lowest energy level possible, you'll have the minimum motion. Okay? So that's where the Kelvin scale comes from. All right? Is that a decent answer to your question? All right. Let me clear this off the scale and go to this. Here's a comparison. Okay? On the Fahrenheit scale, that absolute zero would be down around negative 459 degrees Fahrenheit. I don't want to go there. I don't want to even get close to that.
That's Mars.
Okay, 0 degrees on the Fahrenheit scale is very, very cold. I can only remember maybe a few times in my life that it's even got close to zero, especially here in the southeast. It just doesn't get there much. Okay, I have been off the shore of Adak, Alaska, where it was very cold. It probably was below zero then, and I have been when I was in Nebraska. I came home from finals on December 9th, maybe around December 12th or 15th or something like that. Walked home from taking a nighttime final, and it was so stinking cold outside. I was bundled up with everything I could have, everything. And as I was walking home, my lip felt strange. I said, goodness, what is happening? Am I getting frostbite? My lip was feeling strange, just really strange. I had a beard then. And when I got home, I found out the reason was my breath was freezing on my whiskers as I breathed it. And so then I turned on the radio or television or something to see how cold is it. It was minus 12 degrees. Wow. So I use that as my, maybe minus 15. I use that when I started feeling ice form on my mustache. Now, it may not have been just water vapor freezing. It felt like water vapor, but it's not. No, I didn't say that. Okay. Everything was freezing, by the way. Okay. I knew we were in the minus temperature as well. So yeah, I have been below freezing. So, boy in Nebraska, that happened way too frequently for way too long. All right, the freezing point of water is up here at 32 degrees Fahrenheit. The boiling point up here is 212 degrees Fahrenheit. Okay, on the Celsius scale, named after under Celsius, minus 273 Celsius, or thereabout, that's absolute zero. As cold as you can go. 0 in Fahrenheit is around negative 18 Celsius, so that's pretty cold, okay? And 32 degrees Fahrenheit, which is the freezing point of water, that is, by definition, 0 degrees Celsius. And then the boiling point of water is 100 degrees Celsius. That's what used to be called the centigrade scale, now the Celsius scale. That's 212 Fahrenheit. Now, Kelvin. They dropped the 0 from, so you can't have any negatives. So here was the 0 Fahrenheit, there was 0 Celsius. They dropped the 0 on Kelvin until that's as low as you can go. So everything is positive or absolute. Okay? So that 0 Kelvin at minus 273 Celsius, this will be 255 degrees up here. But if you take the difference between those, you see that's 255 degrees. And then if you take the difference here, that's another 18 degrees. There's 18 degrees. So a Kelvin degree is the same size as a Celsius degree. It's just where you put the 0. You put the 0 way down here for Kelvin, way up there for Celsius. But the degree sizes are the same. And then, since this is 273, since 0 Kelvin is minus 273 Celsius, 273 Celsius would be 273 up from there, so that's 273 Kelvin. And then boiling point is 100 degrees warmer than that, so that'll be 100 K warmer there. Now, two things I want you to notice here. Well, maybe one or two, but one big one. On the Fahrenheit and Celsius scales, notice what we always have? The degree sign. Right. We talk about degrees Fahrenheit, degrees Celsius, but we don't talk about degrees K. We just say K. 273K, 511K, 14K, whatever. No degrees in the absolute scale. Fahrenheit and Celsius, always use degrees Celsius. Okay? Now, this leads us to some of our conversion factors. Because that's what we do in physics, right? We change from one unit to another. We've been doing that all along. Miles to meters and inches to feet and whatever. Okay? Oh, and by the way, I almost missed this. How is your body as a thermometer? Good, bad, or indifferent? Good. Okay, you think so? I use this as a tell me whether I was below freezing or not. You know, that wasn't great, but it gave me an indication. But really, the human body is not too good. And here's what, and this is a lab I used to do, but it made such a mess, and students started not really doing it well anyway, because they knew what the answer was going to be. But I would have ice water here, and I would have as hot water as I could get out of the spigot in the bathroom here. Okay? And I'd have a thermometer in here and a thermometer in there. And have them put their hands in the water, and keep them in there long enough, see what this ice water would be at 0 degrees Celsius. 32 Fahrenheit to 0 degrees Celsius. This, out of the hot water spigot in the bathroom, maybe around 40 degrees Celsius. That would have been, I don't know, better than 100 degrees Fahrenheit. Okay. So, I'd have them feel that. And then I'd have them take them out of there real quickly and put them into more pans of water. So I wouldn't tell them what those temperatures were. I'd tell them, estimate how hot this water is. You know what 0, you know what 40. This is somewhere in between, this was somewhere in between, that was somewhere in between. Tell me what temperature it was. And most of the time, that going from the ice water to this, they feel like that was really warm. Going from really warm water to that, they feel like it was really cold. They would estimate when they were doing it right, and then what they found out when they put the thermometer in, they were really insane. But it's just because this was so much warmer than this, it felt hot. this was so much cooler than this, it felt cold, but in reality, it was the same temperature. Because what our bodies do is measure comparisons. They don't really measure absolute, you might say. So that's what we're talking about here, your body as a human thermometer. Not a very good one. Okay? Now, okay. They're missing a couple slides here, it looks like. So I'm going to, well, let's go back to this one. I want you to tell me what the difference is in temperature between the freezing point of water and the boiling point of water on the Fahrenheit scale. What's that difference in temperature in Fahrenheit? I'm going to have to go to something darker here because that is like, yeah. What is the difference in temperature between those two measures?
Minus 247, 247 degrees.
Okay, wait. 212 minus 32. No, you're not adding. That's not negative 32. That's.
No, I went all the way down to 4.
Oh, don't do that. Don't go that low. And by the way, let me say this too. There is another scale that I don't know of anyone who uses it anymore. Okay? Remember we said the Kelvin temperature measure is the same size as the Celsius temperature. The degrees, so you don't need that, are the same size. It's just where your zero is. Well, they also have a scale that's an absolute scale that uses Fahrenheit degrees. And that scale is called the Rankine scale. Degrees are. I don't know if anyone has ever seen it. I've never seen it talked about any level. That one would be 0 would be down here. This would be positive 459 Rankine. This would be another 32 added to that, another. Yeah. So if you use the same size degree here, that's the Rankine scale. But no one really uses it anymore.
That would be 180.
Ah, very good. This difference here is 180 degrees Fahrenheit. Those are Fahrenheit degrees. What is the difference between these scales? 0 to 100. No. 100, exactly. That's 100 degrees Celsius. And guess what? That's measuring the same temperature range. That ice and that steam are the same temperature. It's just you're using different scales. So this is a key here. What is the ratio between those two? What is the ratio between 180 and 100? I'm going to have to go back to yellow, I think, here.
1.8.
Okay, ooh, that didn't go to yellow. Where's yellow? There's yellow. Okay, here we go. 180, the ratio to 100, and you're absolutely right, that's 1.8. And what's that a measure of? Degrees Fahrenheit for every degree Celsius. 1.8 degrees Fahrenheit, almost 2 degrees Fahrenheit for every degree Celsius. Not quite, close. Now, if you do that, reduce the fraction here. Of course, you could divide out 10 there, and have 18 to 10. What will go into 18 and 10? 2. How many times will 2 go into 18? 9. How about to 10? 5. 9 to 5. Used to be a Dolly Parton song, didn't it? Never mind. Okay. All right. That's the fractional ratio. 1.8 is the decimal representation. 9 to 5 is the. And that's what? 9 degrees Fahrenheit for every 5 degrees Celsius. That's it exactly. Now, if you went the other way, that would be 5 degrees Celsius for every 9 degrees Fahrenheit. They're measuring the same thing, okay? So therefore, if you need to come up with a conversion factor, here's what we do. Now, here's the other difference. You have to get to the same zero. So if you're on the Fahrenheit scale, you've got to subtract the 32 to get you down to 0. Oh, I'm sorry. Add 32 to get you up to the freezing point of water. Here you might have to subtract 32 to get you to Kelvin. So you do have to do a little bit of that so you've got the same zero. I mean, your zeros come out right. So let's see, what can we do here? What conversion factors? If you're starting with degrees Fahrenheit, okay, so many degrees Fahrenheit, you need to multiply it by something. Let me take just a moment here. No. You first have to, before you multiply, you have to subtract. Subtract that 32 off of there, because that's also degrees Fahrenheit. Okay? So, I'm sorry, should have put that parentheses in front. Come back here. Here you are. Okay. So that gets you to wherever you need to be. This is how many degrees Fahrenheit above freezing. That's what that is. How many degrees Fahrenheit above freezing you are. Okay? Then multiply this by 5 degrees Celsius over 9 degrees Fahrenheit. Now, I shouldn't have put the numbers in. I should have put my 2 blocks in. Degrees Fahrenheit down here, so that cancels out that. Multiply that gives you degrees Celsius. And that's how you get degrees Celsius, because the Fahrenheit goes out. What if you're trying to go from Celsius to Fahrenheit? Well, you got degrees Celsius, whatever that is. Now the first thing you do is multiply by 9 degrees Fahrenheit for every 5 degrees Celsius. So your degrees Celsius cancels out. That gets you degrees Fahrenheit. Then you add 32 to it, because that gets you to 0, the same freezing point of water. Then you have to add 32 degrees Fahrenheit. Okay? So that's how you go that way. Now I'm going to write this down. In fact, they're going to show it on the slide set in just a minute. How about Celsius to Kelvin? That one's pretty easy. Let's go back to this slide here. Celsius to Kelvin. Okay, let's see, which is it? Celsius. So we start with degrees Celsius. So start with degrees Celsius. How do we get to Kelvin? Add 273. Start with negative 273, add 273, you get 0. Start with 100, add 273, you get 373. So that's pretty easy. To get the other one, Celsius to Kelvin, start with degrees Celsius, whatever it is, add 273, and that gives you how many K. Notice it's not degrees K, never use degree with Kelvin, just K. That's how you get it. Okay? So, let me erase this, and they will show you what they got. Basically the same thing. But here they are. Now they got them out of order. This is going from Celsius to Fahrenheit is this one. First thing you do is multiply 9 over 5. Why that? 9 degrees Fahrenheit for every 5 degrees Celsius cancels out. And that gives you Fahrenheit degrees, and then you add 32 to get out to that for temperature. Okay? If you're going from Fahrenheit to Celsius, that you start with Fahrenheit, first subtract off from 32 degrees Fahrenheit to get you down to the freezing point of water, or how many degrees above the freezing point of water you are. Then multiply 9 degrees Fahrenheit for every 5 degrees Celsius, so that gives you degrees Celsius. That's how you get that. And then Celsius to Kelvin, whatever Celsius, add 273. Those are your 3 formulas. Those are 3 of the formulas you'll find at the end of the chapter. Know how to use them. In fact, that's going to be the next exercise. How are we doing on time, by the way?
It is
5:32? And we're going to 5:45. So let me know when we get close to 5:45. All right. So let's do example 4.1. Okay. Let's do it right here. The average human body temperature is, anyone know? 98.6, what temperature scale? Degrees Fahrenheit. Okay? What is the equivalent temperature on the Celsius scale? So you're trying to go from Fahrenheit to Celsius. So what's the first thing you're going to have to do? Subtract the 32 degrees Fahrenheit, because that gets you to how many degrees above freezing you are. And then what are you going to do? by 5 degrees Celsius for every 9 degrees Fahrenheit. Very good. And that will give you degrees Celsius, because your Fahrenheit will go out, and that leaves you degrees Celsius. So, first thing we do is what's in parentheses. Please excuse my dear Aunt Sally, whatever she did. Okay? What is the difference between 98.6 and 32? Ooh, okay, 66.6 degrees Fahrenheit. Multiply that by 5 degrees Celsius for every 9 degrees Fahrenheit. Degrees Fahrenheit go out, and this leaves you degrees Celsius. Now, you can either do this with a calculator, which you have, or I'll do it even without one. 3 will go into 9 3 times. 3 will go into this 22.2 times. Well, 3 will go into that again 7.4 times. 5 times 7.4 is 37 degrees Celsius. So there's your answer. 98 degrees Fahrenheit is 98.6 degrees Fahrenheit. It's the same temperature as 37 degrees Celsius. So have you ever thought, what's your temperature? Oh, I'm 40 degrees. Oh, you must be freezing. No, I'm talking about Celsius. Watch these scales. You have to know what units you're measuring. So if 37 degrees is 98.6 degrees Fahrenheit, when it's 100 degrees outside, what are you pretty close to? Well, a little bit more than that, awfully close to 40 degrees. If you're 40 degrees Celsius, you're above 100 degrees Fahrenheit. You can do the calculations yourself if you want to. So just to give you a good thing to measure on. So if you're ever driving in Canada, which maybe you will someday, and their thermometers on their banks are all in degrees Celsius, if you see 37 degrees, you know you're right at body temperature. 98.6, that's pretty hot. I don't know if Canada ever gets that hot. If you see 35, you're still in the 90s. If you see, so it drops on off from there. Okay. Now, 4.2. A bank thermometer displays indicates 20 degrees room temperature. Well, how would a bank know that? They do this sort of crazy. Okay. I wish they'd have written it better. I'm going to erase that ink, and say a bank thermometer indicates 20 degrees Celsius. We won't even say what that is. How do you get that to what is the equivalent temperature on the Fahrenheit scale? So what are you going to have to do? Multiply this by what? 9 degrees Fahrenheit for every 5 degrees Celsius. So that will get rid of your degrees Celsius, and that gives you how many degrees Fahrenheit you are above freezing. But freezing on Fahrenheit scale is? No, freezing. 32. So you add 32 degrees Fahrenheit to it, and you see what you get. Well, I know that 5 will go into 20 4 times. 9 times 4 is 36. Plus 32 would be 68 degrees Fahrenheit. So 20 degrees Celsius is 68 degrees Fahrenheit. What are we here? Yeah, we're 69. 7 or 68. Y'all got it warmed up a little bit to 69. This is right around 20 degrees Celsius. So if you ever see that on the bank thermometer, say, that's pretty pleasant temperature. What we call room temperature. So 68 degrees Fahrenheit, close to 70, that's pretty close to 21 degrees Celsius. Okay. Now, say again? Is it time? Oh, okay. Let's say again? Okay. Let's do example 4.3. Okay? Yeah, this will be a good stopping point. A science article refers to a temperature of, I'm going to erase that other, okay. I thought it was going to use that, but it's not. Science article refers to a temperature at 300.0 K. Did I leave off the degree sign? You don't put a degree sign for K. Okay, very good. Okay, I was right to. What is the equivalent Celsius temperature?
No. 0.
Yeah, equivalent Celsius degree temperature. Okay. What was the formula to get? This is Kelvin to Celsius. What was Celsius to Kelvin? Remember that one? To get to K, you do degrees C plus 273, right? So to get to K, to get to degrees Celsius, subtract 273 from K. So what we do is subtract 273. Now really it's 0.15, but we'll just count it 0.0. Okay? And what would that give you? Say again? 37 degrees Celsius. Very good. And 37 degrees Celsius.
I got 27.
20. Oh, I did too. I just can't do. Late at night, I can't do. Okay, sorry about that. 27 degrees Celsius. Okay? 27 degrees Celsius. What would that be? Warm, cool, what? It's warmer than room temperature. Room temperature was 20 degrees Celsius. So it's 7 degrees Celsius above room temperature. But remember, a Fahrenheit is almost 2 degrees. So rather than 14, let's just call it 10. So that would be probably 78. Pretty close to 78 degrees. Oh, next thing we're going to do is actually calculate it. Let's do that. The B part says, what's the equivalent Fahrenheit degree temperature? Well, we don't have a formula that goes Kelvin to Fahrenheit, but we do have one that goes Celsius to Fahrenheit. So how would we do that? First thing we do is multiply it by 9 degrees Fahrenheit for every 5 degrees Celsius. Remember that 9 to 5, okay? Dolly Parton, okay? And then we've got to add our 32 to get it to degrees Fahrenheit, because this is going to wipe out degrees Celsius and get it. Now this one you will need a calculator, okay? Or you don't have to have one, but it's actually helpful. And you can do it any way you want to. Here's what I would suggest. Oh my goodness, the 10 o'clock scholars, okay? Why did they come so soon? Okay, Parker's here. Did they just make it in under the bell?
Just made it.
What time is it?
It's like 5:40.
41, look at that. Boy, what skates. Okay? That, Zach and Parker, right?
Yes, sir.
All right. Yes. Okay. We're just doing our temperature conversions. This is example 4.3 on page 91 or wherever it is in your book. Okay? So what I would do would be 9 times 27 divided by 5 plus 32. What do you get?
Plus 32. And let's try 80.6.
80.6 degrees Fahrenheit. Let's round that to 81.
Okay.
Okay, because we only had, yeah, this was only 2 digits long, so let's say that. Yeah, they rounded to 81 too. What did we guess it was? Did we say right around 80 degrees? Not bad. Not bad. Okay. You see how you use these formulas? Yeah. All right, good deal. All right. Now, some of you skates that just, oh, by the way, there is on the top of my page 92, it may be something else in your book, there is a closer look at goosebumps and shivering. It's a pretty good read. If you've ever wondered why you shiver when you get cold or gets goosebumps when you get cold, read this. I think you'll find some interesting information. You're probably not going to be tested on it, but still, I find it interesting. So next time we'll start with heat on page 92, section 4.3. Okay? That's where we'll begin next time. All right. What I'm going to do now is pause our... Okay, 3 of you will be on one team, and 3 of you will be on this team. Okay, so you want these 3 and those 3?
Yep.
That's okay? All right.
It doesn't look balanced, but I guess we can do it, yeah.
Okay. So it's just where y'all settled. Okay. Now, attached to each of these strings here is a 500-gram mass. You can see it there. And here, 500-gram mass. Okay. Now, I have a couple of meter sticks hanging around places. If you will, someone come here from each team and measure the height of that mass off the floor at the lowest place it can go. You can get to the other side if you want to. Yeah. And do it to, okay. Oh, wait. Before you do that, what is that mass, 500 grams in kilograms? 0.5 kilograms. Okay? So record the mass in kilograms. 0.5 kilograms. Okay? Now with the meter stick, determine and record the minimum displacement of the mass from the floor in meters. Now do it to the closest tenth of a centimeter, but you have to convert that to meters. Your 0 better be on the bottom, right? Okay? 0 on the bottom? Yeah. Okay, that's centimeters?
Yes.
What did you say again? 41.2. Yeah, but you're different. Yours is different.
Oh, okay.
Yeah. Okay? But you need to convert that to meters. What would that be? 0.4 to whatever she said. Okay?
So, 0.25.
That's the nearest tenth. Okay. So you got your minimum displacement, and that's in meters. It's going to be less than a meter, a point something meters, because this is 1 meter, so you got to be less than a meter. Okay. Now, each team, and you can do this yourself, or you can watch me do it. If I pull the string height here and put it on top of the meter stick, this is something Zach was wanting to do a minute ago, so I'm doing it instead. Sorry. Okay. How high is it from the floor now? 1 meter. So what is the change of the vertical displacement?
Okay, so that's easy.
From what it was there to 1 meter.
So you say
Because it was 23.
0.23.
Okay.
And
And
so
subtract that from a meter.
From a meter. Subtract it from a meter.
1 meter? What's a meter?
1 meter. What's your number you got there? 0.23 something? Subtract that from what?
What is it, sweet?
-1.
0.7.
A negative?
Huh?
A negative?
No, you
No.
subtract it from what?
Okay.
1
Oh, wait.
subtract from the
0.77.
0.77. You got what?
0.687.
0.687. Okay.
And how do we address that?
Meters.
Meters.
Okay.
0 point whatever you said. That's your change of height from where it was to here. Now where it was down here, that was your 0 reference level. That's as low as that thing's going to go in this whole experiment, right? And now it's up as high as it's going to go in the whole experiment. Better be anyway. Okay. Now, what I want you to do is, based on the measurement you just made, what is the gravitational potential energy up here at the top? When it's up here.
Say that again.
What's the
Gravitational potential energy up there. What is the formula for gravitational potential energy? We'll be tested on it Tuesday. You ought to know these things.
No.
GPE? Is someone coming in? Is that-
No, I was just saying, I just looked at it in my book.
Okay, go get it. It's gone.
You want me to go get it?
Anyone remember the gravitational potential energy?
Lacey?
Okay, since gravitational's in the term, what do you think that might be?
No, I'm thinking, and I said no. I can't think of it.
Gravitation.
Potential energy, chapter 3, and it could be right at the end of the chapter where those.
Yeah, that's what
things
it's
are.
all forms. Right. Like the forms. Right here, gravitation.
Potential energy.
Potential energy. Right here. P E equals
MGH.
MGH. What's your M?
mass.
Okay,
Is,
and what is the mass?
500 grams.
Except change it to
5 kilograms.
0.5 kilograms
Mhm.
times what's your G?
Gravitation.
What about gravitation?
That's the G.
What is it?
9.8.
9.8 meters per second
Oh, yeah.
squared. Excellent. And what's your change of height? So that's what we're interested in. G8.
0.687.
Okay, whatever yours
I would say
is.
9.8 what?
9.8 meters per second squared.
9.8 meters squared. Okay.
Meters per second squared.
Per second square,
And what's your change of height? Number 3.
Number 3 is what? 77.
Not 77.
No, number 3.
Yeah.
It's 0.77.
0.77. Okay, decimal point makes a big difference.
77 meters. Okay.
Okay, did you calculate and see what your dBE was at the top?
0.5 times 9.8.
No.
No.
It's
Square.
meters per second squared. The units we got.
Times 0.77. And that would give us 36.97 meters squared second.
Can you round it up? Make that 37 even?
No.
So it's
Let me think about that.
36.975.
Right, okay.
Is that
You
wrong?
did 0.5 times 9.8. That's going to be on the order of 4.9
9.8 times 4.9
Okay.
times 0.77
Yeah.
equals 3.
Ah, that sounds better.
Okay, 77.
Okay, I thought you said. Yeah.
Okay, well, we squared something there, which
Okay.
I did. 3.77.
Okay, no,
Meters
yours
to
will
the
be
second
different. You
square.
had a different delta H.
Well,
You got what?
3.77.
What did y'all get?
I'm doing gravitational.
Potential energy.
Okay, and that's 9.8
Okay, it's the mass.
meters per second.
Mass 1.5 times 9.8 times your delta H.
And then
What's the top?
0.67.
What's the velocity?
That's 6
Okay,
That's
anyway, the answer is 3.77
3.37
meters.
Okay?
Would that be a bit meters?
Huh?
Would that be a 3.77 meters?
Nope. It's kilogram from your mass, meters per second squared from your acceleration, times another meter, so it'd be kilogram meters squared per second squared. Now that has a different name if you want to save some writing.
Okay.
Kilogram meter squared per second squared is also called a
Joule.
joule, exactly.
Okay.
So you can save some writing, just call it a joule.
So where that we go in top?
That's gravitational potential energy at the top. Okay?
That's
3.77.
Now,
Joule. Okay.
all right. Now, what is the velocity here at the top? Look here, look here. What's the velocity here at the top?
That
1
was
meter.
What's the velocity here at the top?
0.
0. It's not moving.
oh, yeah, this is not good.
Okay, not doing anything. So velocity at the top is 0.
Okay.
What's the kinetic energy at the top?
Kinetic energy is 1/2 m times
Zero.
velocity squared.
And the velocity is 0. So 1/2 times the mass times 0 squared, still 0. All right. So what is total mechanical energy at the top?
Total mechanical energy is 3.77 joules.
Absolutely, because mechanical energy is the sum of your potential and your kinetic. And your kinetic is 0, so it's all potential. All right, now, Zach, don't come back too fast or anything, okay? What I'm going to do is release this from the top, okay?
Man, come over here.
Hold on a minute.
All right. Now, what we are asked to do is find the mechanical energy at the very lowest point, the bottom down there. Can anyone tell me what the mechanical energy is down there?
That's what you measure from the floor up.
No, that's the height. What's the mechanical energy down there at the bottom? It's going to be maximum velocity. You got that right. But what is that amount of mechanical energy?
0.5 times a meter.
The sum of velocity and
It's what?
the sum of velocity and
Not velocity, but it's your mechanical energy at the top. Because mechanical energy is conserved. It's always the same. So the mechanical energy up here is the same as
Zero.
mechanical energy down there.
0.
Was it 0 up here? Is that what you said?
No, it wasn't 0 up there. It was,
At the top?
at the top it was.
Oh,
Yeah.
mechanical, 3.77.
Exactly. You got a
Joules.
different number, but you got it.
So it's
That's mechanical energy at the bottom as well. Okay? What's the GPE at the bottom?
Point
How high are you above your 0 reference level down there?
0.4.
It was
No.
30. We was
No.
the point 23. That's what we had.
Yeah,
We
but
was
how
there.
far are you above that?
Above that
when
from
you're at
the
the bottom?
yard
Nothing.
from
No, none of us.
That's exactly where you are. You're at 0.
0.
So you have no change of height down there. So what's your kinetic energy at the bottom?
1/2.
Wait. What's the kinetic energy at the bottom?
0.
Really? It's not moving down there?
It's moving.
Come stick your finger in there.
It's moving. It's moving. Connecticut.
Okay.
I'm sorry, Dr. Fowler. I mean, it was funny what you said, but the third time I had
Last time we had a paddle.
I have it. It's been 30 something years. Okay, so we have kinetic energy at the bottom.
Second? Second?
The 3.3.
Absolutely, because all of your
3.77
mechanical energy,
joules.
since none of it is gravitational potential, all your mechanical energy is kinetic energy. So that would be exactly that amount, right?
Okay.
Now,
The velocity at the bottom.
yeah, now it comes time to do some figuring.
Okay, I'm ready. I'm
We're going
ready.
back out.
Okay.
No,
Now, for just a moment,
no, I want to. Dr. Fowler, what, I'm ready. 1/2 times mass velocity squared.
all right, let's come out and see it.
Okay,
Okay.
then. Thank you.
Everybody walk out here.
I'm gonna go back to sleep now.
Going back in a minute. Don't go too far. Okay. Now, just told me that.
1/2.
Okay. Kinetic energy.
And your
You know how much was it? 1/2
times mass squared.
mass times
Velocity squared.
velocity squared. And we know what that is. That's in the math, right?
Okay.
Okay. All right. Yeah, you have two different teams. So you just whatever your team. Let's solve it literally first. First thing we'll do is we'll get that 2. Multiply both sides of the equation by 2. Right? Right? Okay. And we want velocity. So what else we got to do? Yeah, divide by m. Okay, very good. That got rid of the m. And now what do we got to do? That's velocity squared. We want velocity. Square root. We take the square root of this. So now you just plug in your numbers. Okay? You know what KE is. You just calculate it. And you got two different teams, so don't get together. So 2 times that number divided by your mass. You know what that is. And then take the square root.
Divided by our mass, which is our mass is 0.77.
No, it is.
2 times 3.77 divided by 0.5 equals square
No, you don't square it.
equals 28.42.
Let's go with units now. Units for velocity. Okay. This kinetic energy was, by the way, if you remember, kilogram meters squared per second squared, right? The two didn't have any of them. You divide it by mass in kilograms, so the kilograms go out, and that gives you meters squared per second squared, but then you take the square root of that, and that gives you what? Meters per second. Exactly. And that's what your velocity is measured in. Meters per second, miles per hour, feet per second, yards per second, yards per minute. You know, that's what you measure velocity in. Meters per second. Okay? Now, y'all got that? Now let's go back to the lab. Okay, if you got it written down, get back in here. We're going to do begin with number 6. Oh my, I should have been taking the computer out there. I forgot to take it out there. I don't know, I doubt if you heard me from there, but that's too bad. They should have been here. Right?
Right.
Okay.
We got it on my.
Okay. Now, I will need at least 2 people to help me. We're going to use just one of these. We don't have to use them both. Let's use this one. Why don't you take this? One of you take this one over here. Now, who wants to be the starter and who wants to be the measurer? You start. So put that mass on the top of your meter stick.
Oh my gosh, that's gonna be terrible.
Okay. Now you, with your meter stick, okay, now these first couple, we're not going to write anything down. We got everybody back again.
Yeah.
Okay. I want you to release it from the top of your meter stick, and you give the best guess of how high it goes on your meter stick. Okay? Yeah.
Do it.
Yeah.
Do it. Do it.
Okay.
Pretty close to a meter, isn't it?
Yeah.
Okay, not exactly, pretty close, right?
Okay.
All right, now, y'all stay in your places, okay? With the same mass attached, raised to 1 meter as before, release the mass, but I'm going to peg the mass about 1/3 of the way down the string. I'm going to be right about here, okay? So, and you're going to see how high it goes, okay?
All right, go for it then.
Good, anytime,
I need to get closer. All right.
Do it again.
if you want to.
Did you get it? I do it again.
Yeah, do it one more.
Yeah, all the way up.
About a meter,
Yeah.
about a meter, so you can record that.
Okay.
You got it?
Oh, he go.
You got it.
Try it for me.
No, say about a meter. Okay. Now, I'm going to try to peg it about halfway down. You hold your stick and see about how high it goes.
Ready?
Yeah, anytime. Oh, it's hit by the knuckle. Okay, sorry. I was too close.
That's almost 70.
About a meter. Well, get closer and see. Okay,
Ready again?
about halfway.
Yeah.
Just about a meter. Okay?
Yeah.
Okay, everybody got that?
Yes.
Now I'm going to peg it about 3/4 of the way down. Okay, you
I
ready?
want to come back a little bit.
Huh?
Come back a little bit. I can see
Just right here.
Yeah.
What happened?
it twirled around, I guess. What you
Okay, twist it around the peg.
Yeah.
Now the question is, why? Why did it twist around the peg that time but didn't the other two?
Because you dropped the.
Oh, very good.
across the way
The string here was too short
to
for
make
to
it.
make back to
So
a
it
meter.
circled around. So
Well, why did it keep going?
It had all that built up energy.
Okay, now you're right on the money. It still had kinetic energy because when it stopped at a meter, whenever I pegged it here, it stopped at a meter because all the kinetic energy became potential
okay.
energy. Okay? But when the string was too short, it couldn't reach that height, so it still had kinetic energy, still had velocity. That's right. Very good. Y'all, the team, the class has come out with that first, earliest. Okay?
Yeah. Exactly.
Now,
Lindsay.
okay.
Lindsay.
That's what I did. So I will call her that to the end of this class. If I called her Lisa, she didn't even answer. I said Lisa. And that she was in the room.
Okay.
Okay, so we
Now,
said, I'm sorry, Dr. Parker. Miss Todd, she was talking. So we said because so I can write the answer down.
Okay.
What did you say?
Y'all come up with an answer.
What you say?
He said because of the, what was it again, sweetie? You said the reason why I didn't circle all the way around?
It has built up kinetic energy.
It still had kinetic energy. It couldn't lose it all to potential. So it still had some kinetics. It still had velocity. So it kept moving in the circle. Okay? Now, what conservation principle does this experiment, both parts of this, demonstrate? What was conserved throughout all these experiments? The what? Total energy for sure. But what kind of energy? Kinetic. I thought the kinetic
No,
went to zero up here.
Okay.
Positive kinetic.
Say again?
Positively.
Kinetic was zero up here. It was max down here. Zero again there. So no, kinetic wasn't conserved. Mechanical was conserved, which is the sum of kinetic and potential. Very good. Okay. Now, since the other class isn't here, I would like you to do several more things. Okay. Now, this team over here, your distance from the bottom was 0.23 meters. Okay. The team over here in the margin on that minimum displacement in the margin put 0.23 meters. Okay. Your distance from the bottom was 0.41 meters. 0.413.
So
You put that in your margin over here, and then you, right there, right next to that.
So what
In the
was
margin.
theirs?
0.413, is that what you said?
0.4.
0.413. Okay, now answer all the questions that you just did. First, your delta H. No, don't look.
I gotta get there. What was it?
Zero.
Oh,
0.23.
0.23. So if y'all want to go back to the classroom, you can. We don't need to sit on the floor and stuff. We can go back in there. Since the other class hasn't shown up, shame on them. Okay. Thank you. Oh, I'll take the meter stick. Trying to walk off with my meter stick. Yeah, I see. Okay. Yeah, it's just unbelievable. Oh, I'm gonna get my calculator. I mean my computer. What you lose?
It's not like doing this.
Don't worry about it. I just use that once we get done. That's fine.
What color was it?
It was pink.
Was it yellow?
No, it was
Pink and
pink.
green.
Pink and green.
Pink and green. Some kind of sorority.
I'll just use your pencil. I'll just use yours. Well, you may use when I get done.
You need another one?
He gonna let me use one of these.
Y'all have any more questions about the thing before I shut down Screencast-O-Matic? You know how to do the calculation, you got all the formulas, you got what you need. Okay? Well then, if there's nothing else, I'll go down and shut down Screencast-O-Matic. No more questions?